Okay, so second talk of today is by Saarik Kalia from Barcelona, and he's going to talk about dynamically generated tilt of isocurvature fluctuations.
Great. Yeah. Thanks so much, Anish, for inviting me to give this talk. This seems like a cool seminar series to have. As Anish said, my name is Saarik. I'm a new postdoc at the IFAE in Barcelona. And today I wanted to tell you guys about a recent paper that I put out describing a generic mechanism to produce blue tilted isocurvature through inflationary dynamics. So today's talk is going to be about cosmological fluctuations. So I kind of just wanted to start off by reviewing what we know about cosmological fluctuations and why it's interesting to think about them. So of course, we have good observational evidence that the universe on large scales is fairly homogeneous. You'll oftentimes see maps like this of the CMB, which are telling you that at some spots the CMB is slightly hotter, at some spots it's slightly colder. But these fluctuations are really very small overall, and actually these fluctuations are very small compared to the average temperature of the CMB. So any good theory of cosmology should be able to reproduce these small fluctuations. And of course, one very common explanation is inflation, that there's some period of early expansion which can lead to this type of effect. Another property that we know about fluctuations on large scales is that they should also be adiabatic. And when I say adiabatic, basically what I mean is that the fluctuations are correlated between different components. So that means if this place here has a little bit more photons, and it also has a little bit more baryons and a little bit more dark matter, et cetera. And if this place has a little bit less photons, it also has less dark matter, less baryons, et cetera. And again, any good theory of cosmology should be able to explain that. There's one very simple way to explain it, which is that maybe early on we really just had one component. So if during inflation there was just one field called the inflaton, and everything that we see now comes from that inflaton, then of course any fluctuations that were in the inflaton are going to get inherited by all the different components, and so that's why we'll see correlated fluctuations between components. By contrast, if there were something else which existed during inflation, then and that something else has fluctuations of its own, then it can imprint those fluctuations on some of the components, but not others, and therefore we might see what are called isocurvature fluctuations, basically uncorrelated fluctuations. And we have good evidence that that should not exist on large scales. So such models are somewhat constrained. Now, everything I just told you is really only true on large scales. If you go to smaller scales, then really basically anything is fair game. We actually have no idea what the fluctuations look like on smaller scales. They could be adiabatic, could be isocurvature, they could be small, could be large. And actually, there are interesting consequences to think about if the fluctuations on small scales are indeed large. That can lead to interesting signatures like gravitational waves or non-Gaussianities. So this is a nice scenario to think about. Today, I'm also going to be talking about scalar fields and the fluctuations that scalar fields get. So some of you might be familiar with the statement that scalar fields acquire fluctuations during inflation. And of course, because this is a fluctuation of a field other than the inflaton, which is also present during inflation, then these fluctuations are isocurvature fluctuations, just as I described on the previous slide. So all this is to say that isocurvature fluctuations or enhanced fluctuations in general are not just something you can think about, but really something you should think about because scalars are very generic in lots of different new models of new physics. A little more specifically, the statement is usually that if a scalar field is very light, so if its mass is much smaller than the Hubble scale during inflation, then we usually say it gets isocurvature at all scales, both small and large. And as we saw, constraints on large scales from the CMB tell us that such scenarios are somewhat constrained. You have to be careful if you're giving fluctuations on large scales. On the other hand, if the field is very heavy, if its mass is much higher than the Hubble inflationary scale, then typically you expect no isocurvature fluctuations at all. So basically, you typically expect either to be constrained or get no interesting signals at all. However, sometimes you can live in this happy medium if the mass of the field is roughly comparable to Hubble during inflation. Then what you'll get is a blue tilted spectrum. by blue tilted, I mean that it has very small fluctuations on large scales, but very large fluctuations on small scales. So you can avoid constraints while still getting interesting signatures out of it. So that's a nice regime to live in. Will have nice consequences, and it's also allowed. But of course, this requires some coincidence of scales. And in particular, if you like to think about very light dark matter, maybe this is a kind of untenable scenario, or very light fields in general. This might be an untenable scenario for you. Of course, there are various games you can play to get around this condition. You can try to do some model building. Say I have a field that I want to be light at the end of the day. I can give it some effective mass during inflation, some big mass which is comparable to Hubble, and then I can take it away later, and then it can get this blue tilted spectrum, but still have a light mass at the end of the day. So these kind of games can be played, but it requires some extra ingredients. The talk I want to give today, there are really two main points I want to make in this talk. The first is actually that getting this blue tilt is not as hard as it might seem. And actually, this can arise rather naturally and rather generically through the inflationary dynamics of the scalar field itself. There are two conditions you basically need to satisfy in order to get this. One is that the scalar field should have some non-trivial potential. And actually, the particular potential is not super important. There's a fairly wide class of potentials that this can work for, so you're not restricted to any one potential. And then the second condition is that inflation shouldn't last too long. We'll see that that's an important one as well. So if you have those conditions, then actually you can get this blue tilt fairly generically. The second thing I want to argue is that this mechanism that I'm going to describe is actually a good production mechanism for scalar dark matter. And in fact, it'll give you a fairly predictive relic abundance, which is going to allow us to draw lines in parameter space to say, okay, dark matter has to have these couplings in order to be dark, in order to be dark matter to get the right amount of it. And so that'll give us predictive parameter space targets. In particular, towards the end of this talk, I'll focus on quartic dark matter, and I'll show you what that parameter space looks like for quartic dark matter, and I'll actually draw that line for you. But first, I just wanted to sort of schematically draw a picture for you of what this mechanism looks like and how exactly this works. So today I'm going to be considering a scalar field during inflation, which has some non-trivial potential, and I want to think about what its dynamics are and how that could lead to this blue tilt. So let's suppose that my scalar has some non-trivial potential. Much like the inflaton, this scalar has some slow roll solution to it, which I'll tell you in a second what the condition for that solution is. But there are generically going to be some regions of the potential which satisfy the slow roll condition, and there are going to be some regions which don't, which I'll call fast roll. So let me suppose I'm in the scenario where I begin inflation in the fast roll regime. Then what happens? Well, as the name suggests, I will begin to proceed very fast down the potential until I reach the boundary between this fast and slow roll regime. Then again, as the name suggests, from then on, I will proceed very slowly. What all of this means is that for most of inflation, I really spend most of inflation near this boundary regime here. In other words, that means for most of inflation, the slow roll condition is marginally satisfied. That's kind of the key point that we're going to tap into. Okay, so now what is this slow roll condition that I've been talking about? It turns out, as we'll see in a bit, the slow roll condition is that the second derivative of the potential should be less than Hubble squared. Of course, the second derivative of the potential is basically like an effective mass for the field. And so the upshot of all of this is that the dynamics naturally give you a scenario where the effective mass of the field is right around Hubble. It's very close to Hubble. And remember, that's precisely the condition we needed in order to get a blue tilt. So this is a basic explanation of why you generically expect a blue tilt for if you have some non-trivial potential. So the outline of my talk will be roughly as follows. In the first part, I'll focus on what happens during inflation. So at first, I'll focus on what the condensate, the average value of the field is doing. I'll basically flesh out that picture that I just showed you, what actually happens as this scalar rolls down this potential. In particular, I will tell you what the slow roll solution is, and I'll identify what the relevant slow roll parameter is. Then in the second part, I will talk about the perturbations of the field. And I'll show how you actually get a blue tilt for the spectrum. I'll show how a potential leads to a blue tilt. In particular, I'll tell you that the size of the blue tilt will be related to the slow roll parameter that we've calculated in the first part. Then in the second part of the talk, I will focus on what happens after inflation. So what happens during radiation domination. Now, the mechanism I just explained to you will leave the scalar field with some relic abundance. And we can track what happens to that relic abundance as radiation domination goes on. It'll leave you with some late time abundance, which can actually be the right amount for it to be dark matter. And so we'll track through what parameters give us the right parameters to be dark matter. In particular, you'll note that because this the first part of the dynamics relied on an attractor solution, then the final relic abundance is independent of the initial conditions of the scalar. And in that sense, the benchmarks that we're going to get, the particular parameter values that will predict the right amount of dark matter, those are going to be relatively robust to initial conditions of the scalar field. And again, I'll show you what exactly that line looks like in the case of quartic dark matter. And then finally, if I have a time left over, I'll say some few words about what happens to the density perturbations as radiation domination goes on. They acquire like an order 1 factor, so it's not a big change, but it's good to understand. And of course, I'm more than happy to answer any questions if people are interested. Please just feel free to chime in during the talk. Okay, so let's start off figuring out what happens during inflation. So I want to suppose that the scalar is going to be mostly homogeneous, so it consists of a condensate, the average value, along with some small perturbations. This is the similar type of scenario that you would consider for the inflaton. And it's actually a well-motivated scenario because, of course, even if you start off with a fairly inhomogeneous configuration for the scalar field, inflation will kind of zoom you in on one patch, which is homogeneous. And so you'll fairly quickly get into this scenario where you have mostly a flat homogeneous configuration. Okay, so we're going to start off just by talking about what the dynamics of this condensate are. And let me define this parameter that I'm going to call alpha, which will be the second derivative of the potential over h squared. And then throughout this part, I'm going to try and track the dynamics of alpha, what happens to alpha as time goes on. As we'll see in a little bit, alpha will turn out to be the slow roll parameter, actually. Good. So the condensate satisfies this equation of motion. This is basically just the Klein-Gordon equation for a homogeneous field in an expanding background. This is, again, the same type of thing that you would see for the inflaton. I should say that in this talk, I'm just going to take inflation as being exactly de Sitter, so Hubble will just be exactly constant during inflation. Okay, so let's suppose that I first start off with alpha being very large. If alpha is very large, that means that Hubble is small compared to the potential. So I should be able to neglect this second term here. And then you can see that basically the field is going to oscillate in its potential. In fact, I shouldn't completely neglect this term because that term actually causes causes a little bit of energy loss. It's still a friction term. And so that's going to cause the scalar to redshift. It'll redshift with some equation of state W. But the important thing I want to point to is that this redshift, if you characterize it in terms of the number of e-folds n, then it's the energy density as well as also this parameter alpha are going to decrease exponentially as a function of n. So when alpha is much bigger than 1, then your alpha will decrease exponentially as a function of n. That's the important point. Okay, and so I've also been talking about this slow roll solution, the slow roll regime. So what is this slow roll solution and when does it actually apply? So the slow roll solution is when I can neglect the first term in this Klein-Gordon equation. And then you can see that the slow roll solution follows from there. Again, this is the same type of slow roll solution you would see for the inflaton. And I can ask, when is this slow roll solution valid? Well, it's valid when the first term is smaller than the second term. If you write that in terms of alpha, you'll find that it's exactly just alpha is less than 1. So indeed, alpha is the relevant slow roll parameter in this scenario. This slow roll solution here applies when it's less than 1. Now you can rewrite this slow roll solution in terms of alpha and solve it as a function of n, the number of e-folds. And it turns out what you'll find is that alpha goes like 1 over n, basically. So the long story short of all this is when alpha is large, then it decreases exponentially. When it's small, then it decreases like 1 over n. The coefficient of this 1 over n is going to depend on the potential, as we'll see in a second. So this here is now a numerical evolution of alpha over the course of inflation for two different potentials with basically two different exponents for phi that I've taken. And we see exactly the behavior that I explained. So at early times, the scalar is oscillating and redshifting. So alpha in particular is decreasing exponentially as a function of n. But then at late times, it's going like 1 over n. These dashed lines here are supposed to be the analytic predictions for what alpha should be. So the upshot of all of this is that indeed, as advertised, alpha is going to spend most of inflation being slightly less than 1. In fact, you kind of generically expect it to be 1 over the number of e-folds that have passed. The coefficient here, as I said, will depend on the potential. Generically, for generic potentials like this blue one, which is a quartic potential, you expect like an order 1 coefficient here. But in principle, there are potentials that can have larger coefficients like this one. So for this one, it's actually quite large even by the end of inflation. Now, as we'll see in a sec, the relevant value for alpha is the value of alpha at horizon crossing for whatever mode you're interested in. So in particular, if we want to know about what the CMB, the tilts of at the CMB modes look like, that tilt is going to be governed by alpha around -60. So you can see that the alphas around -60 can be quite large, much larger than they are at the end of inflation. Okay. Yeah, so we can also, now that we kind of understand this scenario, we can outline some necessary conditions that we're going to need for the potential and also for the starting value of the potential in order for this scenario to work. Basically, these boil down to just I should start in the fast roll regime, right? So that means I basically have to start high enough up the potential that I'm in the fast roll regime. There should exist some slow roll regime that I can roll to. And in particular, kind of the most important condition here is that I should begin rolling towards that slow roll regime. So that's that condition here. And this is kind of, again, the most important condition on the potential, which is going to restrict certain types of potentials. This only works for a large class of potentials, but not all potentials. In particular, like a cosine potential is not going to satisfy this condition. So you won't be able to do this for, say, like an axion, but a quartic potential will. And so we'll see this mechanism works well for a quartic potential. And then finally, I should just, the entire time, I should never, this scalar field should never be dominating inflation. It should always have less energy density than the inflaton itself. Good. Are there any questions on any of the condensate dynamics that I've talked about yet? Okay, if not, then I will move on to talking about what the perturbations are doing. So now I want to track these perturbations, del phi k. And for starters, for simplicity, let me forget about the potential. And so the story we're going to find of how the perturbations behave without a potential is exactly the same story that you would find for the inflaton, but it might be instructive to just review it really quickly. So the perturbations will satisfy this equation here, which again is just the Klein-Gordon equation, basically, in an expanding background. I'm going to make a quick change of variables, which is, again, a fairly common change of variables to make in context of inflation. I'm going to work with this f, which is basically just a rescaled version of del phi, and I'm going to think about things in terms of conformal time tau. If you cast things in that way, then the equation becomes a little simpler. It looks like this. Now we can already see different regimes of what should happen. At early times, when the mode is still sub-horizon, then this kappa or this k tau is very, very large. So we can neglect this term, and we see that the equation just behaves like a harmonic oscillator. So at early times, the perturbations are just oscillating. In particular, you can as we actually heard about in the previous talk, you can you should set some initial conditions for the field. These are typically the Bunch-Davies initial conditions, which look like this. So at early times, they're oscillating. At late times, we can ignore this k squared part. This is when the mode is now super horizon, larger than the horizon. And typically what you would find for the inflaton or for a free massless scalar field during inflation is you would find that this delta phi k is constant. The f has to go like 1 over tau, and that means that delta phi is essentially constant. Okay, now I want to add back in the potential. What happens when I do that? That gives me an additional term here, which has a similar form to this 2 over tau squared term, but just a different coefficient, which now depends on my potential. And you'll see that basically just that you can actually see the coefficient of this potential is related to this alpha parameter that I've defined. And that'll actually just shift things a little bit by alpha. And ultimately what you'll find is that delta phi, now rather than being constant outside the horizon, it's now going to decay exponentially, where the exponent of this decay is determined by this alpha parameter. By the way, I should say that this treatment here actually doesn't even applies for just a mass. So a sort of trivial potential. If v is just m squared phi squared, this exact same treatment holds, and you would again find exponential decay outside the horizon. Good. So what we've learned is that perturbations, when they're outside the horizon, then the presence of a non-trivial potential causes them to decay. And the decay, again, is governed by this slow roll parameter that I've called alpha. Basically, the upshot of all of this is that if I want to talk about, say, the power spectrum of the perturbations, then any given mode is going to be damped by the integral of alpha for the entire time it's outside the horizon. So here in this integral, this n star is when the mode crosses the horizon. This is when k tau equals 1. And then nRH is just the reheating, which I've taken in most of my plots to be n equals 0. So again, they get suppressed the longer that they're outside the horizon. Now, the key point and the reason that this all gives us a blue tilt is because longer wavelength modes exit the horizon earlier, and therefore they spend more time outside the horizon. So if longer modes get damped more and shorter modes get damped less, then that is a blue tilt. That is more power at smaller scales. So that this is precisely the result we wanted. And in particular, we can see actually that the blue tilt is governed, the size of the blue tilt is governed by the size of alpha, specifically the size of alpha at horizon crossing for a particular mode. Okay, so we can even see what that looks like, see an actual plot of this. So this is the isocurvature power spectrum for the same two potentials that I showed you in a few slides ago. And you can see in both cases, we get some amount of blue tilt here. As I mentioned before, the tilt at any given point is related to alpha at that, it's related to the alpha at horizon crossing. So we saw that the alphas around like minus 60 or so were relatively large, and that's why we can see a relatively large tilt at CMB scales. Again, as if alpha is larger, then the tilt's going to be larger. That's why this orange one has a much stronger tilt than this blue one. But even for the blue one, we can see it really gains like an order of magnitude over many scales. I should say I'm comparing this now to various existing constraints on the isocurvature power spectrum from the CMB, Lyman alpha, and even at smaller scales from ultra faint dwarfs. And so I can find scenarios where I'm indeed avoiding these constraints at large scales, but I can get very enhanced power at small scales, which could have interesting results. Finally, this dotted line, I'll come back to at the end of the talk. But yeah, that I'll explain what that means in a bit. Okay. Are there any questions on anything I've said in the talk so far about what happens during inflation?
I don't see any questions.
Can I ask one question? Can you hear me?
Yes, go on.
Yes, yeah.
Okay. So, if I understand correctly, this means that whatever you have proposed so far only works when Hubble rate is constant during inflation, right? I mean,
So
there's a fixed Hubble parameter.
Sorry, what?
Yeah, I mean, when there is only a fixed Hubble parameter.
So my calculations have assumed that there's a fixed Hubble, but in principle, you can also take into account a varying Hubble as well. In fact, let's see. If I go back to here, when I derived this slow roll condition alpha less than 1, I derived that by doing this comparison. Basically, when you take the second derivative here, I was acting the second derivative on the top here, which gave me a v double prime. That's how it became alpha less than 1. And so that's what the scenario would look like if Hubble were exactly constant. If you now want to incorporate the fact that Hubble is changing too, then the derivative can also act on the denominator here. And so you actually get another slow roll condition. It turns out that slow roll condition is precisely the usual first slow roll condition. It's precisely epsilon less than 1, where epsilon is the usual epsilon of the...
This is my actual question, that if Hubble parameter will vary during inflation, then this means that your alpha is nothing but eta, right? Eta, we usually define eta in terms of double derivative of this potential divided by Hubble parameter, which is more or less equal to potential under slow condition. So, I mean, then your alpha is nothing but eta. Is this the case?
So yeah, exactly. If this were the inflaton that I was talking about, then yes, this alpha would be precisely eta. Probably, I probably should have mentioned that. But importantly, it's not because this is a subdominant component. So Hubble now is not connected to the value of to what this scalar field phi is doing, and that gives you some different results. For instance, in inflation, oftentimes the slow roll parameters are small up here. Like this is where slow roll happens up higher up the potential, and it becomes fast lower down the potential. Here we're getting an opposite effect because Hubble is not connected to the value of the field. So the fact that this is not the inflaton does change things a little bit.
Okay, thanks.
Yes, but that's a good question. You can also account for the slow roll parameters of the inflaton, so the fact that Hubble is changing, and basically this just gives you another slow roll parameter, which is just the usual slow roll parameter. And so essentially, if alpha is bigger than epsilon, then you can forget about the fact that Hubble is changing, right? And looking at these plots here, alpha is like 0.1, like 10 to the minus 2, 10 to the minus 1-ish. So for most of inflation, alpha is larger than the values of epsilon that we expect. Okay. Yes, thank you. That's a good question. Were there any other questions before I move on? Okay. Then now I'll talk about what happens after inflation. Okay, so during radiation domination. So the story we left off with in the previous part, the scalar field ended inflation with some energy density in it, in particular all in this condensate. And so if the scalar is long-lived, then this energy density will evolve, and it'll give you something, some amount, some relic abundance, which is around here today. And in particular, there are parameters for which this can be exactly the right amount to give you dark matter. In fact, and we'll see that basically this sets some relationship between the potentials of the parameter, what values of the potential give you the right amount of dark matter. And recall that because this whole story relied on a slow roll attractor solution during inflation, then none of this depended on the initial conditions of the scalar. So that's kind of a key point I'll come back to in a couple slides. All of this only depended on the inflationary parameters, like Hubble or the length of inflation. Okay, so how would I actually go about calculating the energy density of the scalar field? I should say from this point on, it's actually easier not to work with the scalar field itself, but rather to work with the energy density rho. This is basically because as the scalar field starts oscillating and things, it will become a lot less homogeneous, and the scalar field itself is doing complicated things, but the energy density is doing simple things. So we can track how the energy density evolves over the course of inflation. Of course, it should start off the same way, over the course of radiation domination. It should start off the same way it ended inflation, which was frozen. So not redshifting at all. And if I want it to be dark matter, then it should end up redshifting like matter, redshifting like e⁻⁻3. What happens in the middle, in principle, depends on what exactly the potential that I'm working with is. So from this point, I have to pick a potential. So let me pick a quartic potential, something fairly common, fairly well motivated. And then it turns out that actually in this middle part, the scalar will redshift like e⁻⁴. It'll go like radiation when it's dominated by the quartic term. And then when it's dominated by the quadratic term, then it'll go like matter. So these are the three phases that quartic dark matter would go through. And of course, I can go through the exercise of seeing if I start radiation domination with whatever I left off inflation with, and I run through how much dark matter, or how much of the scalar field am I left with, and how can I get that to be exactly the right amount to be dark matter. So again, enforcing this correct abundance will lead to some relationship between the parameters of the potential. In the case of a quartic potential, it leads to some relationship between the mass of the field and the coupling lambda. And this will give us a benchmark in parameter space. We can draw a line in parameter space and say dark matter lives here. So actually, I wanted to take a quick aside to talk about some other benchmarks of dark matter models that are in the literature. So you might be familiar with, like, for axion dark matter, there's this misalignment mechanism, which comes with some concrete line in parameter space that it predicts. And for like Friesen dark matter, there's also some sort of line too. And these lines are important experimental benchmarks. They're these are important targets for experiments to be working towards. In fact, this plot on the right here is from a recent Domik M paper where they hit this Friesen line, and that was a big deal because they got to one of their benchmarks. Now the reason that these benchmarks are taken so seriously is, one, because the models that predict them are relatively simple, but also because there's some degree of robustness to these lines. They're somehow insensitive to some aspects of like initial conditions. So like for the axion case, this line.
Yes,
sorry,
we have 5 minutes left.
Oh, okay. All right. Yeah. So in the axion case, this line is sort of for a generic value of the initial axion, and for the Friesen case, this is insensitive to the reheat temperature, for instance. So I want to argue that the line I'm about to show you is basically exactly the same. It's a robust benchmark because it's insensitive to initial conditions of the scalar field. Okay, so now I'll show you what this line looks like for quartic dark matter using this mechanism. I should preempt one common criticism, which is that the parameter space I'm about to show you is fairly technically unnatural. But this is common for a lot of dark matters and a lot of dark matter models and inflationary potentials. So if you get over that, then this is I think a quite interesting and strong result and a good part of parameter space to look at. So this is what the parameter space for quartic dark matter would look like. This blue line here is telling you basically the exact potential, the exact parameters, which would give you the right amount of dark matter for Hubble of 10 to the 10 GeV and 80 e-folds of inflation. I'm drawing various other colored regions here as well, which are various other constraints on this mechanism. So like this red region up here is where the power spectrum that I showed you a few slides ago would be too large. It would hit one of those constraints. This orange region here is where you would have too much of this dark matter sitting around during BBN, so that would be constrained by N effective. And this pink region is, if you care about this, this would require initial conditions which are Transplanckian, where the field starts off at higher than M Planck. Also, these gray regions here are various late time constraints from like self-interactions or from structure formation. But you can see that there's a decent amount of nice, well-moded parameter space for quartic dark matter. These dashed lines here are what these lines would look like if I used a different Hubble parameter, if I used 10 to the 12 GeV instead. Okay, so the last thing that I wanted to quickly touch on is what happens to the density perturbations as radiation domination goes on. What happens to them after inflation? So the story I told you about the perturbations at the start really just told you what they look like at the end of inflation. It turns out as you go further on, they'll acquire like an O of 1 factor. So it's not a big game changer, but it's important to understand. As with the relic density, here it's actually easier to track the perturbations of the density rather than the perturbations of the field itself. Okay, but in order to do that, you can apply this simple separate universes argument at large scales, which is basically to say that the universe is composed of various different patches. Each of these patches will end inflation with a slightly different amount of the scalar field of dark matter, and perhaps also some slightly different curvature perturbation from the inflaton itself. And then I can basically each of those patches will just follow the same dynamics as the zero mode that I showed you for the different phases of evolution that I showed you for the zero mode. And so the end result will be just modified by the slightly different initial conditions. So I didn't go through the full calculation of the relic density, but if I had written out a full formula for what the relic density looked like, it would have told you that the final density was related to the density at reheating and also to the Hubble constant of the whole universe. Now a slightly varying initial density will, of course, create a slightly varying final density, right? These are essentially isocurvature perturbations because these are telling me if I had slightly more or less dark matter in certain places, if the scalar field was doing different things in different places, then that only affects the amount of final dark matter I have. However, if having different Hubble, different values of Hubble in different locations is essentially analogous to having different gravitational perturbations in different places. So the perturbations that lead to changes in Hubble from location to location are precisely the same perturbations that lead to different amounts of photons or different amounts of baryons in different locations. So these perturbations are adiabatic perturbations. You can actually read off that the adiabatic perturbations should have this 3/2 coefficient in them, which is the coefficient you expect from standard cosmology. So long story short of this all is that basically the isocurvature perturbations acquire some factor of some order 1 factor of 3/8 on large length scales. So the plot that I was showing you several slides ago, this is accounting for the factor of 3/8. That factor really only applies at large length scales, so really only to the left of this dotted line here. But I draw it as a dotted line because that line depends on the mass of the field and also on the particular model. So this is for a mass of 10 eV for quartic dark matter. Exactly here. Okay, so finally, I'd just like to